Force and motion, wherein we look at the concepts of forces, laws of motion, equilibrium, accelerating systems, and analyzing systems using force analysis. First, we look at the concept of force. Put simply, a force is an influence, whether a push or a pull, an influence that can change the state of motion of an object. For now, when we say state of motion of an object, we're talking about the velocity of an object. So force is an influence that can change the velocity of an object. An object may be subject to one or more than one forces. Even if the object is subjected to several forces, the object will behave according to the net force. The net force is the summation of all the forces acting on the object. F net is equal to F1 plus F2 plus F3 and so on. Note that force, as you can see in the equation, force is a vector quantity. It has both magnitude and direction. Therefore, you not only need to take note of the magnitude of the forces, you also have to take note of their direction in your analysis. Thus, in getting the net force, you have to use your force, your vector addition, your component method to get the net force. The unit for force is Newton. 1 Newton is equal to 1 kilogram meter per second. Newton gave us three laws of motion as far as forces are concerned. First, we have the first law of motion. First law of motion, if no net force acts on a body, the body's velocity cannot change. So our definition goes back to what we have previously mentioned. Force is an influence that can change the state of motion of an object, that can change the velocity of an object. Therefore, if there is no net force, there is no force acting on the body, the velocity will not change. If F net is equal to 0, the velocity of the object is constant. And of course, the reverse of that, if the net force is not 0, there is a net force acting on the object, the velocity of the object will change. It is not constant. Consequently, if the velocity is constant, that means the acceleration is 0. If F net is equal to 0, the acceleration is 0. If F net is not equal to 0, the velocity is not constant. That means the velocity is changing. There is acceleration. The acceleration is not equal to 0. So the first law of motion, even though quite simple in terms of statement, has several implications. Next, we have the second law of motion. If the first law of motion implies that there is a relationship between the net force and the acceleration experienced by the object, the second law of motion gives us the relationship between the two values. For constant mass, that is to say, we consider the mass to be constant no matter what happens to the motion of the object, no matter what happens to the object. So for constant mass, the net force is equal to mass times acceleration. Hence the unit kilogram meter per second squared. Hence the unit Newton. So again, second law of motion, for constant mass m, F net is equal to mass times acceleration. And finally, we have the third law of motion. Some books refer to this as the law of action and reaction. For every action, there is an equal but opposite reaction. F reaction is equal to negative F action. If you have one object and that object pushes another object, F action, the second object will react by applying F reaction on the first object. And if you compare the two forces are equal in magnitude but they are opposite in direction. F reaction is equal to negative F action. Before we go to force analysis, let's look at first some forces that you might encounter in this course. So some common forces for this course, for basic physics. First, we have weight, variable capital W. Weight is basically the gravitational force acting on the object. Using our equation from Newton's second law of motion, F is equal to ma, the weight of an object is equal to mg, where g is the acceleration due to gravity. For locations on or near the surface of the Earth, the acceleration due to gravity is negative g, or negative 9.8 meters per second squared. So magnitude of g is 9.8 meters per second squared. As long as the object is on Earth and the object has mass, the object has weight. Weight is equal to mg. Next, we have the normal force, variable capital N. When an object presses against a surface, the surface reacts by applying or producing the normal force. It's basically the reaction of the surface to prevent the object from passing through the surface, from passing through it. The normal force is always perpendicular to the surface, and of course, out of the surface, the direction of the normal force. So if the object is placed on a horizontal surface, for example, due to the weight of the object is pressing into the horizontal surface. The horizontal surface will produce a normal force perpendicular to the horizontal surface, so vertical, and out of the horizontal surface. So as you can see in the drawing, the normal force is vertically upward, going out of the horizontal surface, perpendicular to the horizontal surface, to try and prevent the object from passing through the surface. If the surface is diagonal, the same definition of the normal force will still apply. The normal force will be perpendicular to the diagonal surface, and of course going out of the diagonal surface. There's no set equation for the normal force. The equation for the normal force will depend upon the situation given by the problem or situation. Next up is friction. Small f. Now, there are actually two types of friction. You have sliding friction and you have rolling friction. As far as our course or discussion is concerned, we are talking about sliding friction. There are two types of sliding friction. You have static friction, F sub S, and you have kinetic friction, F sub K. First, we look at static friction. Static friction arises rather to oppose impending sliding motion between two surfaces that are in contact. So first, you need two surfaces that are in contact. For example, as you can see in the figure, you have an object placed on a horizontal surface. So the surface of the object and the horizontal surface are in contact. And if there is impending motion, the motion is just about to happen, static friction will arise to prevent the motion from happening. The direction of static friction is always opposite that of the impending motion. Okay? Static friction opposes the impending motion. So it is opposite in direction. For the magnitude of the static friction ranges from 0 to a maximum value. The maximum value that static friction can have is given by mu s n, where mu s is the coefficient of static friction. The coefficient of static friction is property of the two surfaces that are in contact. So each pair of surfaces will have its own value of coefficient of static friction. For example, you have wood against wood surface that has its own mu s. You have wood against aluminum surface that also has its own mu s. Now, mu s, coefficient of static friction, does not have any unit. It is a unitless quantity, and it ranges typically from 0 to 1. Note that mu s can never be less than 0. That is to say, it cannot be negative. But depending on the circumstances, mu s may be greater than 1. But the typical values for mu s ranges from 0 to 1. So don't be surprised that in some problems, mu s will be greater than 1. Next, we have kinetic friction, F sub K. If static friction opposes impending motion, kinetic friction opposes existing sliding motion. The motion is already happening. The object is sliding along the surface with velocity v. Kinetic friction will oppose that motion. So, kinetic friction is always opposite the direction of the velocity. As for the magnitude, unlike static friction, kinetic friction is relatively constant in magnitude. F sub k is equal to mu k n. Mu k is coefficient of kinetic friction and property again of the surface pair that we have. Typically, mu k ranges from 0 to 1. So as you can see, just like mu s, mu k does not have any unit. It is a unitless quantity, and typically it ranges from 0 to 1. Again, mu k cannot be negative. It cannot be less than 0. But depending on the circumstance, it may be greater than 1. Typically, it ranges from 0 to 1. Now, regardless of whether you have static friction or kinetic friction, you will notice that sliding friction is always parallel to the surface. In both figures, the surface is horizontal, therefore, the friction is also horizontal. And N here, whether you have mu Sn or mu Kn, N is the magnitude of the normal force. And lastly, we have tension, variable capital T. Tension is basically reaction to being stretched. If you have a string, rope, wire, or similar object and it is stretched, the object reacts by applying tension, pulling at the objects attached at its ends. So if, say, you suspend an object from a string as shown in the figure, due to the weight of the object pulling it down, the string is being stretched. The string will react by applying tension T. And that's it for now. In the next video, we'll look at force analysis or analyzing systems using net force. So thank you for watching.